Okay. Sorry for that. Oh. It's complicated. No problem. Sorry for me that I didn't unmute. So, okay, like to wrap it up, like humans, right? We build representations and so on, and we want to use this, and we learn very efficiently. So this means that something happens in our brains, and we can be so efficient into understanding our own bodies and understanding the scenes and understanding shapes and so on. So why we are interested in geometry. So again, taking a look into from a human point of view, biological systems are able to basically judge the 3D scene level topology and also object level poses and sizes. And I guess you had already talks where they talked about like the object-centric representations, which is quite interestingly, and I put also a reference there that these are actually mapped in different areas of the brain in humans. So there is no single representation. There are different abstractions of the scene level and the object level, and then they are parsing them. And we combine this information according to what actions we are doing. And what we can say, and we have been learning, I guess, if we did also computer vision, is that animals and humans, that they have lenses, they use projective geometry in order to map the 3D scenes into the retinal images, right? So you take from your eyes, you project what you see, the 3D world, into 2D images, right? And what happens is that in order to understand what you are looking at, both animals and humans have this constant experience of this geometry, of this projective geometry, and how they can understand their embodiments based on these perceptions. Obviously, there are also other signals that we are deploying, but it's super interesting if you think about it. And there's also a very big debate that I also included there for the interest of discussion maybe later on, that in Plato's perception geometry, and in particular the Euclidean geometry, that it is the so-called natural geometry, is supposed to be innate. So Plato would argue that this is something that we come with a built-in functioning of being able to perceive geometries, while Poincaré and Einstein argued for actually that this is something that you acquire with experience. In any case, it's something super interesting to consider, and it makes us very efficient to have these sort of geometric biases and geometric representations that allow us to learn very fast. And effectively, in my research, I basically want to explore robotic embodied intelligence, not necessarily from the language level downwards, but I am also interested for the other way around. So how you can start from bottom-up approach. Because I don't know what is your opinion, but I think that grounding comes from the geometry, and then language comes on top as a semantic layer. So if we look at the structure on different levels, what we would like to use and accelerate our learning processes and our planning processes is to have a good representation on top of which we can do efficient and safe learning. We want to be able to effectively coordinate the robot with, especially if we are talking about this sort of bimanual mobile humanoid robots with 20 degrees of freedom. You want them to coordinate with respect to themselves, but also the task that they have to solve, and swiftly navigate in the environment without needing millions of demonstrations, and effectively do active exploration in order to balance objectives of understanding the scene, but still being efficient in solving a task that they have to do. So you don't expect a robot that is a mobile manipulator in your house to spend 15, 20 minutes just scanning the environment in order to map everything. So there should be like a stopping criteria somewhere there. So in the first part of the talk, we will see how we can use topology of constraints in order to learn to act safely. And for that, of course, neural representations have been very actively used in the last 2-3 years or so, or even more. And in particular, we started looking into signed distance fields, because naturally in robotics, signed distance fields is a good objective in order to formulate obstacle avoidance objectives in control and for planning. Therefore, it makes sense to try to use neural representations of these implicit functions in order to lift them into more high-dimensional and complex manifolds, like, for example, this 20 degrees of freedom robot, where we change the deep sign distance field architecture into one that can afford basically to compute the distance field of the robotic body at any configuration of the robot. So it can interpolate basically on all possible poses. So instead of training one distance field per object, you're basically training for the articulation of the robot. And additionally, we added a regularization in the training objective, where it would understand and switch between representing an object that you are interacting with a Euclidean ball into collapsing into the manifold that represents the object geometry. These allowed us to get these very nice level sets on the manifold of the robots, and also we have done the same also for humans. And this is the difference of the level sets that we obtained with our training approach compared to a deep sign distance field that doesn't really care about too many level sets or doesn't include the regularization or ECOMAN that was another prior work in this direction. And what is super efficient is that you can query this neural network in batch, in real time, from a number camera, trying to estimate human poses. And then you want eventually to use this for safe planning for the interaction. And you can see this as a safety layer also when you want to interact with humans. So in order to learn how to interact safely especially if we consider dynamic environments, we naturally looked into safe reinforcement learning, because it's not always easy to have like explicit dynamics for this kind of problems. And instead of treating the problem as if in most safe reinforcement learning approaches, where you would put like the constraints as a cost, or you would create a safe set that you will basically filter out possible actions, what we did, we considered that we have an affine control system and some constraints that may be either the innate inherent constraints of the robotic system, or they may come from obstacles in the environment that you want to avoid. And we created the constraint manifold, the one that if you also put slack variables, you can also have also inequality constraints. And what we did, we tried to change the action space of the robot and map it on the null space of this constraint manifold, such that all your actions are always tangent on this manifold. This means that you strictly restrict your actions to locally never violate the safety constraints. And this is like a swift transformation that you can have, subject that you have, of course, the constraints, and you can also deploy the learn distance fields, because you can have access to the Jacobian and then learn, for example, to do some sort of dynamic manipulation in narrow environments like this bookcase, and then transfer it in the real world without much loss on performance, because basically you have this transformation, this topological transformation all the time. And what is super interesting is that we can use it to also interact in the proximity of humans. Here in this task, the robot had to deliver this cap upwards. So this is one of the objectives of the task. So it is considered as a constraint. It has to deliver it in this position, while avoiding collisions with the robot itself, with the table and the human that it is doing random actions. And we have done this several times, and I think only once in many experiments the robot overturned the glass, but it never actually collided with the human or with the environment. So in some sense, we prioritized also these constraints, such that the weight of the achieving the goal has like the lowest effect in the constraints. And of course, this is one way of seeing these problems for the low-level control, but usually we need to guarantee some sort of safety, even when we are one level higher, when we are doing planning. So then a question is, how can we represent objectives in the proper topological space such that we can ensure that we can do efficient planning? And For this, it is a line of works that we have done from last year, starting from energy-based models, where we have proposed learning energy-based models as implicit priors, or if you want, cost functions for optimization. So we assume that we have multimodal demonstrations of tasks going to different multimodal goals, and we learn a landscape of these demonstrations so that we can use it if you take a planning as inference perspective as a prior, or if you take a trajectory optimization perspective as a cost in your optimization. And we are interested in these energy-based models because they can capture multimodalities in data. They are composable because they belong to the exponential family. And for example, you can have a distance objective that you can very easily also represent into as an exponential, basically, and then add them up and have both learned and hand-designed objectives and do optimization. And finally, what is very good in this case is that you can learn these task level costs on the task space and use differential kinematics to switch. So you don't need to do learning from demonstration with kinesthetic teaching, which is also favorable. So you have like an object-centric representation of the costs. Now, I will not go to many details about how we originally trained these energy-based models, but given now that we have diffusion models and we have a better way to actually acquire the scores, that it is basically the energy that we are interested in, we recently proposed the SE3 diffusion fields, that it is basically an approach that takes the classical diffusion training pipeline and lifts it into the SE3 manifold, such that you can operate with points that belong into SE3. And the process is similar to the one that we use for training diffusion models, only that we take into account basically the curvature of the manifold and deploy Lie algebra. The way that you are training this, so you do the whole diffusion process. So you do we train with denoising score matching, and then for doing the inference, we do the inverse diffusion process in order to extract poses that are in the low energy regions. And one very good example on where this kind of multimodality is needed is when you see at grasping. So if you want to decide how to move to grasp an object and then how to place it, there are many different ways of how you can interact with objects regarding of what is your end goal, right? So it would be very nice to not have to decompose all these things into distinct optimization tasks and having a single pipeline to do this. And given that we can plan basically with this diffusion process, and there is actually research from the 90s on diffusion planning in robotics, in SE3 diffusion, you can have basically trajectory optimization using Langevin dynamics with diffusion processes in order to do trajectory optimization. So what we do, we learn with a model that takes into account the SDF of the object that you want to interact with. In this case, we have this kind of mug, let's say. You have the representation of the gripper as a point-based representation. You learn jointly a feature space training basically on the SDF of the object and additional features for the gripper. You also induce the noise level of the diffusion process, and then you flatten the feature space and you train on the energy. You try to predict basically the energy. And then what you can do, you can train this for different types of objects in order to get diversity of possible grasps. And once you have this, then you can connect it to the trajectory optimization that I said. So in trajectory optimization, you try to minimize a weighted sum of costs. So now if we do this planning as inference approach, we can redefine the cost as being this energy with respect to also taking into account the forward kinematics of the robot for mapping from robot configuration to the actual task space. And then you frame motion generation as an inverse diffusion process where basically we define a desired target distribution that it is analogous to the exponent of the original objective that we had for the optimization. And this allows us to effectively sample not only for grasp, but sample using the forward kinematics, the whole trajectory of where the robot should start from an initial pose to reach and grasp an object in different variations. Of course, the number of samples is also a hyperparameter here, but you can eventually then add collision avoidance objectives that may not have been trained for. So here we only trained for grasping while we hand designed the distance field-based costs with the obstacles, and you can basically very nicely generalize and do it as long as you have, of course, a representation of the scene. So you need a pose-based representation, and you can also combine it with placing objectives. So with respect to how the object is placed in the scene, you can, let me go back here. You can place it effectively by this joint single pipeline of optimization without having to have decoupled. First, let's sample a few grasps, and if these grasps succeed, that is good. And then we have to do the placing and so on. Here you can have a single pipeline. But of course, this is very local. And as I said, I am interested in mobile manipulation. So we also did recently a different work into the perspective of how we can grasp in cluttered scenes, especially if we consider a mobile robot that has only an embodied camera with a partial view of the environment. And in general, as a human, if you see, for example, here I see this glass and I have the mental model, and even if I don't see everything about the robot, I am able to complete the information in my brain. So we wanted to have something similar for the robot, such that the robot doesn't lose too much time in exploration. And you will see in a while in the last part of the talk how this actually connects. So we want the robot from any random viewpoint to be able to understand the scene and grasp objects, even with partial information. And for that, we reimagine grasping as rendering, taking advantages of neural surface rendering approaches. So what we do, we train a pipeline that basically take the advantages of scene reconstruction approaches based on convolutional occupancy networks, and as I said, surface rendering methods, in order to learn to reconstruct the scene and then complete the scene, on top of them sample grasps, and then evaluate with the grasping as rendering approach possible 6 DOF grasps. Let me go a bit step by step. So you have the, you need to complete the scene from a partial view. This is the TSDF of the scene. You pass it through the 3D convolutional encoder. You take the 3D feature volume, and then you have the occupancy network that learns to basically do scene reconstruction. And I think that this is pretty well known. And the question is, like, how can you extract the right features now for grasping, given that you have so much multimodality in this scene? So what we do, first of all, is that you need to have also diversity in terms of grasp. So it makes sense to actually, and this is not new, also in terms of efforts in robotics, in robotic vision, to try to complete scenes in order to sample grasps. Now that you have the idea of neural surface rendering, you can do array marching, you can complete the point cloud and take a newer point cloud with more complete information so that you can sample even grasps in areas that you have not seen. And you can even add constraints. So we are extending currently this work with semantics so that you can even, for example, restrict where you want to grasp, given that you have completed the scene. Now, what is very difficult in robotic grasping is effectively inferring good 6 DOF implicit values. Like, how can you really understand that the grasp is good? Usually what happens is that we split up the process of grasp detection by being implicit in the 3D positions, and then we are regressing the SO3, which is very, very difficult. And we know already with the different representations of orientations, this can become quite challenging, right? So what we opted here is for a complete 6D representation that it is fully implicit, by considering that the grasp itself has virtual cameras. So, and what you're trying to do is you try to render what does the hand see when it is looking at an object, at the side of an object. And what do you do there? You then can extract features that are relevant to the interaction of the surface of the object with respect to the robotic hand, kind of a complementarity thing, such that you can use then these features as the representation of the 60 graph to learn to detect if a grasp is good or bad. Okay, and this comes also with additional benefit because you are also training there for the reconstruction of the local surface, which is way more fine-grained. You even get better reconstructions on the global level, which makes sense because in the end of the day, this kind of representation will give you even grasps that are not in collision with the environment. So how this works, the robot goes in a pre-grasp pose, it scans the scene, just one view, it completes it, it samples grasp, and then pass it through the grasp detection approach with the grasping as rendering method, then executes the grasp with the planner. And here you can see an example in the, this was a simulated environment from VGN that we also worked on, which has some hundreds, thousands of objects that are being simulated in millions of scenes. And eventually we kind of get state-of-the-art performance with respect to other implicit or semi-implicit approaches. And we also can see the performance in the real world with the robot, where you can effectively hear only with a static, for example, setting. The robot looks at the scene, completes and does the decluttering of the scene. But we can also now move the robot around, take any partial view of the scene, and also decide, for example, with which arm it makes sense to grasp an object, given that we have completed the scene, so we can actually reason about also reachability. So this is nice. Of course, one issue is the rendering time, that it is much higher than a simple point cloud-based representation that doesn't do any rendering, even if we have optimized it a lot, also given the advances that come from computing rendering. And the last part that I will go very briefly, just to show you the complexity of acting in the real world, how we can leverage both scene and object level information in order to actively explore, but still being able to execute a manipulation task. So again, we have the setting where the robot is equipped with the embodied camera. Now it starts from an unknown position in the room, doesn't know anything about the room except for an area in which we suppose that an object is lying. So the question here is, how can we actively perceive and explore, given that we have occlusions and so on in the scene, while being able to execute a task? Now, if we look in active perception work, usually your goal is to only do scene reconstruction, while in grasping, either you have a very static setting, and you explore quite a lot till you find a right grasp, but this, you can imagine, is very inefficient for mobile robots, that they have to move around and they can spend a lot of time exploring instead of doing the task. So we need time and energy efficient solutions for mobile manipulation robots. So as I said, let's consider the setup. We have the robot with just a notion of a very broad, let's say, bounding box of where an object that could come from language description, for example, pick up the red mug. That it is, I don't know, on the table, or we know there are many works that they actually give this sort of goal specification. So you have this naive understanding of the goal, and then you try to explore, find the object, and effectively grasp it and transfer it, and so on. And during this exploration phase, the agent, the robot, builds a TSDF, so assigned distance field representation of the scene, trying to balance active perception, so for revealing more and more scenes, but also more and more grasps, and then eventually deciding where should I stop in order to execute a grasp that seems to be actually possible to succeed. And we formulate this as a model predictive control, so an optimal control problem. Given our initial idea of where there is the bounding box, still consider that the robot doesn't know anything else apart from the bounding box in the beginning. We sample reachable base goals based on reachability maps from mobile manipulation. This is a pretty common practice in order to reach specific locations. And we use these possible sub-goals as a way to sample trajectories of the base placement and also of the camera poses, because we want to reveal as much information as possible. So as I said, this is framed based on reachability, how we sample the goals, and the cameras are basically random. So we move the torso up and down and basically the camera orientations. And we try to balance information gain from reconstructing the scene that we also penalize with the distance that you need to travel in order to reveal more information. And our other planning utility is the executability that has to do with only revealing grasps that are above some threshold of grasp quality. And their reachability score, and also how much distance does it need the whole body execution to spend in order to find the grasp. And by doing it in a model predictive control fashion, you can be reactive to new 3D information being revealed in the environment. And so in essence, you sample candidates, you collect the utility across the path. So you do the whole model predictive control kind of accumulation of costs in the descending horizon. And you also can reason about collisions, because the more you reveal about the scene, you can do fast collision checking and take this as an additional cost into your planning objectives, how many grasps and what is the reachability utility of the grasps. These utilities basically try to infer how much information will be revealed if I move my robot in a specific pose in terms of head and base. The arms, in theory, you could have done also whole body kind of motion, but the arms are irrelevant for this kind of task. But effectively, if you wanted to avoid an obstacle, you should also consider the task level. So here you see, if I move my robot, what is my expectation of new information to reveal? And this is the reachability map of both arms of the robot. So you also reason between both arms, the reachability of both arms. If I am here, what is the probability of finding an IK solution for executing a grasp? So we did a lot of ablations. I will not go to all the study here, but what was very, very interesting, it was that when you were restricting your grasp detector, so the grasp detector here was VGN, and VGN is basically mainly biased to predict top-down grasps. And in this setting, if you were restricting the top-down grasp to have like only side grasps, the balance between executability, basically the reachability, and the information gain was very evident, the impact that it had on the planning process. And this is an example of the next best view kind of planner, that it is only what is my next basically best pose. So the agent usually kind of does zigzag motions around the table without having a clear objective of finishing up the task once a good grasp is found and the agent is in a good pose in order to grasp an object. And we transferred it also in the real world. So we had an initial phase of exploration for locating the bounding box with respect to, so we deployed mask former, I think, for the languages, for the semantic kind of detection. And after that, the agent was only moving with a point cloud based information. You see also, I think it's very small there, the information gain that it discovers in order to grasp objects that are in clutter. So we can rearrange this thing, put also more clutter around, and the agent is able to detect, do the semantic detection of the object that it needs to grasp, and then explore a bit and eventually go and perform the task. So I will let this, and I will be done now. Yeah. So this is a work, of course, done with my collaborators. Yeah, all the shout out goes to them. And as a final takeaway, I think that we need to reconsider how we use the structure of the problems and effectively how we can use geometry and geometric manifolds. I think this is also something to consider now with the pre-trained models that are basically scaling down the problems into the 2D space, which in my opinion will not allow generalization into the 3D space unless we combine them with some additional geometric prior. And I think that we should focus on more challenging kinematic structures like mobile manipulation, because they are a very good example for achieving embodied intelligence. So yeah, thank you for your attention.
Time for questions. When you're reasoning at a scene level, do you break the objects, like decompose the scene into individual objects?
In both works, no. It's in the neural network approach, you assume that this has been done inside the network from the way it has been trained, and the basically you also impose some sort of equivariance from the way that you train and generate the data. Here you only assume that you know the bounding box of the single object that you want to find and grasp. So once you go towards this object and you start querying grasps, then it goes up to the planning stage to plan collision-free grasp without caring about the notion of the objectness of the other objects. And it's, I mean, it would be interesting to think of whether it would be needed or not. Chad, you wanted to ask something? Oh no, I thought you were.
No, I'll ask you. So when you're but let's say you have to, when you graph, you have to think about the next action.
Yeah.
Next action. How does that change? How do you think about that? Can you incorporate that longer term, longer, right?
Yeah. So how we now cope with that? We actually had another work where we are composing the energies of different objectives for solving a more long horizon task. And what is the problem there is that you cannot have all the energies being equally balanced. So you either have a decision making on a higher level that basically decides which kind of objectives are currently active and what should be the weighting of these objectives. So we basically change the temperature of these energy-based models, which is also something that you can do on the diffusion level, which is also kind of nice. So when you are training and you get basically the gradient of the energy, is something that you can also incorporate. But you need a higher level of reason with that.
Thank you.
I have one question. So it's about the last comment that you made, specifically pre-training, where people are typically focused on 2D observations. So
and discrete actions.
Yeah. What is stopping us from that pre-training?
I mean, we could extract data potentially from stereo cameras and assume that the network inherently will extract the information in a similar way that humans do. Again, the question is, how can we effectively get all this data to do it? And do we really need it? It's a question. So I would, for my point of view, the pre-trained visual language model have a very great application on this higher level of designated which object, how the goal should be specified in the 2D space, and then you can have another layer that had the geometric basically processing of how I will execute it in the 3D world. So it's also a question of efficiency. If we put potentially an inductive bias on these models, it would be also interesting to see if they can really correlate well. But right now, I guess what is happening is like the attention focuses on some features on the 2D plane that have also some semantic meaning. And then most of the tasks are basically very tabletop. So we don't really do the leap to the next phase, but it's, I mean, it's research. So this is our job. Thank you.